In this video, I'm going to look at what you need to know for the Reactivity Series topic. And the starting point is, what is meant by the Reactivity Series? You got a definition to learn for that. And that definition is an order of how reactive a group of metals are with metal, steam, oxygen, and each other. In other words, it's kind of like a ranking of a lot of different metals from the most reactive down to the least reactive. And these are the metals you're meant to be familiar with. The most reactive metal in your reactivity series is potassium, and as you go down you get less and less reactive. So we've got sodium, calcium, magnesium, aluminium, zinc, iron, and finally the least reactive one you need to know about is copper. So now the question is, how do we know that this is the correct order of the reactivity series? How do we know that potassium is most reactive? How do we know that copper is the least reactive? Basically, the way we do that is by doing lots of reactions with these metals and see how they compare to each other. See which ones react more quickly than each other, see which ones have more violent observations than other ones. That allows us to put them into a correct order from most to least reactive. The first reaction that we'll compare all these metals for is their reaction with oxygen. Now, before we look at the specific reactivity, you need to know a little bit about how you'd practically do that reaction with oxygen. Essentially, it's going to involve a Bunsen burner to provide some heat to provide energy for the reaction to take place. But normally that reaction takes place within a crucible on top of a tripod with a lid on top. So here you got your crucible, which is a little bit like a small pot with a lid on it, which has your metal inside on top of a gauze and a tripod with a heat source, a Bunsen burner underneath. The reason we've got the lid on top is to allow the heat to get trapped, to allow enough energy to build up to allow the reaction to take place. Though what we will need to be aware of is we need to lift the lid up occasionally to let some new oxygen into the reaction to allow the reaction to complete. Now, what you need to know for each different metal for this reaction with oxygen is how their observations compare to each other, and also the chemical equation for that reaction with oxygen. These are the observations you have to learn off. It looks like quite a lot, but there's a lot of similarities between them. Most of them will form white solids whenever you react them. Just the observation that takes place to get them to the white solid often is different. So with potassium you get a lilac flame, it ends up forming a white solid. Sodium has a yellow flame, burns to form a white solid. Calcium a red flame to white solid. Magnesium a bright white light to a white solid. Aluminium, it only really burns when it's a powder form. The solid form of it doesn't really, the lump form of it doesn't actually burn that well. It needs to be a powder, but again forms a white solid. Zinc's a little bit unusual in that whenever you burn it, it initially forms a yellow solid, but eventually once that cools down it goes back to being white. Iron is a little bit different. You get orange sparks with it. It doesn't really burn with a flame, just sparks, and it's a black solid as opposed to a white solid. And then copper is a little bit different still. It's not very reactive. It doesn't actually burn, but it does go black, and it causes the Bunsen burner flame to turn a little bit blue-green. And these are the chemical equations you need to also know for these reactions. As a basic pattern, you're always going to get the metal plus oxygen to form the metal oxide. Now, the formula of the metal oxide you need to work out for yourself using a swap and drop using your periodic table, and then it's a case of balancing the equations. So you can see them, I'll not read them out, but you can see all the different equations you're meant to know for the reactions of the different metals with oxygen. The next reaction we'll use to compare our different metals of the reactivity series is a reaction with water, more specifically cold water. First of all, how we do that reaction, practically speaking, basically it's a case of dropping the metal into a container of water. For some reactions we might want to trap the gas produced to test it, and for that we can use an upside down test tube on top of a filter funnel filled with water that allowed the gas to be trapped. Which we can see in the apparatus here. We've got an upside down test tube filled with water. Any gas produced by this reaction in water will bubble up through the upturned filter funnel, collect in the top of the test tube, and you could do a gas test on that to prove its identity. Once again, we do need to know the observations and the equations for this reaction of a metal with cold water. Now, with the observations with water, here's where we'd start to see some differences in the reactivity of the different metals. What we actually find is it's only the top 4 metals of the reactivity series are reactive enough to react with cold water. We will see no observations for aluminium, zinc, iron and copper. Nothing will take place. For the remaining metals, we see the potassium is most reactive, has the most observations, and we get slightly fewer observations as you go down to magnesium. Potassium moves on the surface, fizzes, produces heat, crackles, the metal disappears, you get a colour solution, and you'll sometimes see a lilac flame. Sodium is similar but maybe slightly less reactive, moves on the surface, fizzes, melts into a ball, heat is released, metal disappears, and the colour solution. Calcium is a bit less reactive still. It fizzes, it sinks and then floats. Heat is released and a cloudy solution is formed at the end. And magnesium is barely reactive enough to react with water. You get a few bubbles produced over a long period of time. In terms of the equations for those reactions, the basic equation is that a metal will react with cold water to produce a metal hydroxide plus hydrogen gas, and you need to be able to convert that into a simple equation as described for each metal in the table. The next reaction we look at for each metal is the reaction with steam. Now, steam is still water, we've seen that before, but more specifically it's the gas form of water. It's got a higher temperature, so it's turned into a gas. The reason we look at this reaction is that because steam has got a higher temperature than cold water, it allows some of the less reactive metals that we've seen haven't reacted with cold water. We now do see reaction with them for steam. In terms of how you do that reaction, it involves a slightly more complicated looking piece of apparatus. Essentially, we've got a boiling tube with a piece of metal in it. At the bottom of that boiling tube, we've got a piece of mineral wool which is soaked in water. And what we're going to do is we're going to heat both the metal and the mineral wool. The metal will get hot enough to start to react, and heating that mineral wool, which is damp with water, will produce steam, and the steam is going to move over the metal to allow the reaction to take place in a steam environment. The reaction will take place and any gas produced, as we'll see in a second, is going to travel down this delivery tube through a beehive shelf up into a gas jar filled with water that will allow any gas produced to be collected by downward displacement water, which we could then maybe check using a gas test. For the observations of that reaction, potassium, sodium and calcium are clearly reactive enough to react with steam, but they would be a bit too reactive to do safely, so we wouldn't normally do these reactions in a school lab. However, we do have observations for magnesium, aluminium, zinc and iron. Once again, we find copper isn't quite reactive enough to do the reaction with steam. The observations for magnesium are white light, white solid produced, heat released, gas produced. Aluminium is similar, powder burns to form a white solid, heat released and gas produced. For zinc, the powder burns form a yellow solid that turns white when cooled, heat released and gas produced. And finally for iron, the powder burns red hot to form a black solid, heat is released and gas is produced. Now there are some similarities with those observations to the observations for the reaction with oxygen, and there's reason for that. In this reaction with steam, even though you might expect it to have the same kind of equation as for water, because remember steam is just the same thing as water, we actually get a slightly different product formed. We don't form the metal hydroxides which we get with the reaction with steam. The metal hydroxide you make actually breaks down at high temperatures and leaves us just with the metal oxide. So the actual reaction with steam we end up with is a metal plus steam reacts to give you a metal oxide plus hydrogen gas. And we see that difference reflected in the equations for those reactions. The metal reacts with water, which is steam, to produce the metal oxide plus hydrogen gas. Now from these three reactions, with oxygen, water and steam, we have been able to build up a picture about which metals are most reactive and which metals are least reactive. However, there is a slightly more informative way, a slightly better way of working out the actual order of reactivity, and involves you reacting the metals with each other in a type of reaction called a displacement reaction. The definition of a displacement reaction is when a more reactive metal displaces a less reactive metal from a compound. Now the word displace just means push out. So what we're going to see here as a pattern is if you're comparing a more reactive and less reactive metal, the more reactive metal, if it's by itself, is able to push out a less reactive metal if the less reactive metal is in a compound. Now it's easiest to see that if we look at a couple of examples. Now let's look at the reaction of magnesium with copper sulfate. So we're trying to compare the metals here, magnesium Mg and copper Cu. If we look at our order of reactivity according to our reactivity series, we see that magnesium is more reactive than copper by quite a few places. According to our rule for what a displacement reaction is, that means that the more reactive metal, magnesium, should be able to displace or push out the less reactive metal copper from its compound. So copper is going to get kicked out of copper sulfate and magnesium is going to take the sulfate part of it for itself. It's only able to do that because it is more reactive. It can steal the sulfate and push out the copper. And that would give you the following products: magnesium sulfate, so magnesium has taken the sulfate part, and then copper is left by itself. It's been displaced from its compound. Now, that displacement reaction is a pretty common one, and you can be asked for the observations for that reaction. So the first thing we've got here is that copper sulfate at the start is blue, and it's normally dissolved in water for the experiment to work well. So the blue solution is going to be used up, and what it's replaced with is magnesium sulfate. Now, magnesium is just a group 2 compound compared to a colourful transition metal compound. It's actually a colourless solution. So we'll see the blue solution turning colourless. The magnesium metal at the start is used up and no longer there at the end, so it'll look like the grey metal will disappear. And we're forming copper in this reaction from copper sulfate, so it's going to be produced as a red-brown metal. Now, lots of these reactions take place in a similar format to this, where you've got a solution of a compound reacting with a metal. It doesn't always have to be like that. We've got one example of a solid metal reacting with a solid metal compound, an example known as the thermite reaction. In this reaction, we've got solid aluminium metal reacting with solid iron oxide. If we compare the two metals, aluminium is further up the reactivity series than iron. Therefore, the aluminium can displace the iron, push it out from its compound. That will leave you with aluminium oxide. So aluminium has stolen the oxygen from the iron, and iron is left by itself. That's called the thermite reaction. It's a very exothermic reaction and has a number of very distinctive observations. The reaction is very exothermic, it produces a lot of sparks, and it's so hot at the end that the iron produced is actually molten and in the form of liquid iron. So by now we've got a pretty good picture of the order of reactivity of the metals and some observations which allow us to understand or be able to recognise why some metals are more reactive than other ones. We need to have a little think about why that is though. So why are some metals very reactive? Why are some metals very unreactive? And it's easier if we kind of take one example of an equation and kind of analyse that. If I take the first reaction we wrote down for potassium with oxygen, if we focus on the metal itself, basically what's happening here, and in each case for every other reaction, is that a metal is going into a metal compound. And if you think about metal compounds, it's a metal joined to a non-metal, therefore it's an ionic compound. So to try and condense it down to the simplest form possible, in all of these reactions, a metal is turning into a metal ion. So in this case, we've got potassium turning into potassium plus because it is losing one electron. So when we're talking about the reactivity of metals, basically what we're describing is how good those metals are at turning themselves into positive ions. Or in other words, how good they are at losing electrons. A more reactive metal will be much better at losing electrons than a less reactive metal. So reactivity is determined by the tendency of the metal to lose electrons and form positive ions, and more reactive metals lose their electrons more easily than less reactive metals. The last section that we need to look at is on the extraction of metals. One of the consequences of the fact that metals are very reactive is that if you want to find the metal to make use of it, you're very rarely going to find the metal in the ground to dig up as the pure metal. What will have happened is that the metal will have already reacted with the oxygen in the air around it, and what we need to do is to get the metal back from the oxygen compound. So for example, potassium oxide will contain potassium, and if we take the oxygen away, we are able to get our metal back. Now, the technique we use to take the metal back from its metal oxide, or its ore, depends on the reactivity of the metal itself, and we'll use different methods for different metals depending on their reactivity. So we go from bottom to top. The first metal is copper. Now copper is the least reactive metal in this reactivity series, and what that generally means is that it will barely react with anything in the atmosphere of the Earth. So you can actually find lumps of copper underground to dig up without having to do anything to them to get the metal pure. The next two to look at are zinc and iron. They're slightly more reactive than copper, though not by much. They will have reacted with oxygen in the atmosphere of the Earth, and that means they'll be found as zinc oxide or iron oxide in their ores. We do a reaction known as a reduction to get the pure metals back, and that's normally done with either carbon or carbon monoxide, and those are processes which are built upon in later topics. so extracted by reaction with carbon C or carbon monoxide CO. The remaining metals are too reactive for that technique, and we use a different technique which is more successful with those more reactive metals, known as electrolysis. And electrolysis has a whole topic devoted to it later on in year 12.